Okay, Unit 2, Whirlwind. So, electrochemistry. What is electrochemistry? It's the study of how chemicals exchange electrons. And there has to be a transfer of electrons in order for it to be electrochemistry. So if I have a transfer of electrons, something is losing electrons, which is called oxidation. Something is gaining electrons, which is called reduction. By the end of the unit, we learn that, or by the middle of the unit, we learn that loss of electrons happens at the anode and gain of electrons happens at the cathode. Now the thing that is gaining electrons might not actually be the cathode itself. Do you remember that? So if your Sn2 plus is gaining 2 electrons to become Sn solid, well, so that's not going to work. Yeah, sure. I might have a carbon probe here in my solution of Sn2 plus. I don't have any tin. So my tin is not my cathode, but rather the carbon is the cathode. And this is happening at the cathode. And my carbon will be plated with tin by the end of the reaction because I'm forming tin. So this is gaining electrons, reduction, half reaction, true. It's happening at the cathode, true. So it's happening right here. If that had a number on it, and this numerical response, you put that number down. And what is the cathode? Well, it can't be the tin 2 plus, because cathode has to be an electrode, which has to be solid. It can't be tin, because I don't have tin in here. So therefore, my cathode is now carbon graphite, because that's the stick that's in the tin solution. Everybody get how GERC doesn't necessarily mean that it's joined together. Do you remember that? That's a little tiny fine-tuned thing. Okay, so this in its most simple form is what you did in Chem 20 or even Science 10, where you learned how sodium has 1 valence electron, chlorine has 7 valence electrons, and sodium will want to transfer to fill its shell. So what this has to do with is stability. It still has to do with stability. Okay, a spontaneous reaction happens because they become more stable. This would happen spontaneously because sodium, without that electron, therefore it has a +1 charge, and chlorine now becomes chloride with the extra electron. Now we've got just table salt, more stable, full valence shells. So what this picture diagram in Chem 20 stroke Science 10 equates to for us in Chem 30 is Na neutral, has lost the electron and become Na plus. And if it's lost the electron is produced, so it is a product. We also look at how this is balanced, and that is balanced, neutral, neutral. Not always neutral, sometimes +2, +2, but they have to be the same. And therefore this is losing electrons, which is oxidation. The Cl, I'll just do the atom for a second here, becomes Cl minus, and it did that by gaining an electron. Yes? But we all know that Cl doesn't exist as itself if it's an atom. It exists as a diatomic molecule, so Cl2. Therefore, if I have 2 of these, I'm going to get 2 of these. So that becomes a big 2 because they're separate. These are attached. This is separate. And each of them gain electrons, therefore 2 electrons are gained in total. So I've got this Cl2 plus 2 electrons becoming 2 Cl minuses. This is a gain of electrons, which is reduction, and that reaction will happen at the cathode. So what will I see at the cathode? Well, this one's a little harder. I'm going to see bubbles disappearing. That's a bit hard to do. The green gas will become colorless. That you would see. So this is a green gas, and it becomes colorless. What you'd see the sodium metal becoming sodium ions. Happy days, everybody? No problems? Okay, so we also talked about how Leo is a reducing agent and Gur is an oxidizing agent, because if it is gained, it causes something else to be oxidized. If it is reduced, it causes, I forget what I just finished saying because I was reading at the same time. But anyway, Leo reducing agent and Gur is the oxidizing agent. It's opposite of what you think because it causes the other thing to do it. Everybody happy? Okay. So how do you originally this had to do all with oxygen. So we had our iron oxide pile becoming small iron solid. So this is a reduction of the pile, therefore it was reduced. What is it lost? It's lost oxygen. So sometimes you can define loss of electrons as oxidation by the fact it's just lost oxygen. That's why it's called oxidation. Gaining electrons reduction because the pile has reduced. Everybody okay with that? Okay, so I think that was it. That was like our introduction day, really. And then we did a variety of reactions where we looked to see if you could identify if it was gaining or losing electrons. So for example, I gave you Mn plus O2 goes to MnO, and I asked you to write the oxidation half reactions, the reduction half reactions for this. You probably, by this point in the course though, are looking at oxidation numbers, more or less. So you'd probably go oxidation number 0, oxidation non-zero, -2, +2. This goes from 0 to +2, so therefore this is a, what's it doing? Losing electrons, which is oxidation. This is gaining electrons, which is reduction. If it's a reduction in number, it's a reduction. Okay, that's like this short little reduction in number. 0 to -2 is a reduction in number. That thing is reduced. Okay, so reduction. And then writing the half reactions for these things. This is unbalanced. Our net reaction will be balanced. So the Mn became Mn2 plus. How did it do that? It lost electrons. How many electrons did it lose? 2 electrons. So there's your loss of electrons, oxidation. This is the reducing agent. Your O2 becomes O2 minus. How did it do that? By gaining, this is the tricky part, gained 2 electrons, right? And each of them gained 2 electrons. So actually I'm going to form 2 O2, 2 minuses, and I have 4 electrons gained in total now, not just the 2. Everybody okay with that? So those are my 2 half reactions, my oxidation half reaction, my reduction half reaction, gain of electrons is reduction, oxidizing agent. And now I can write my net reaction by looking at my electrons, right? 2 lost, 4 gained, they don't equal. In your little beaker, you should have as many lost as gained. If the cafeteria has given out and lost 12 scones, somebody better have gained 12 scones. Okay? So same thing here. If I'm losing 2, I must be gaining 2. Oh, no, gaining 4. So I must be losing 4. So I multiply this whole thing by 2. So I end up with 2 Mn's, 2 MnS, 2 pluses, and 4 electrons. So 2 magnesiums and oxygen go to 2 Mn and G. Sorry, we're doing Mg. 2 pluses and 2 O2 minuses because the electrons canceled out. This is called your net. This is the same thing as 2 magnesium oxides. And we've ended with the same balanced equation that we should have if we balance that like we did in Science 10. Okay, so these very simple things, I know you can balance using Science 10, but the whole point is that this gets a lot harder, and you know it gets harder. You know I'm going to have H pluses in here that we can't do by Science 10 anymore, and therefore this is the simple way of showing, hey, it's the same thing, it adds up to be the same thing, you should be comfortable with it at this point. Happy? Okay, so those are the simple examples I gave, and you can find these, you can make them up. Right? So if it's not in your data booklet, and you can find them on your data booklet. Yes? Okay. So we did that a lot. We talked about rusting, and how rusting is a natural redox reaction in which your iron ions, it's a mixture of Fe your iron solid becomes your iron ions. It's a mixture of Fe2 plus and Fe3 plus. They'll often tell you the compound that it becomes if they want you, because sometimes they express it as a hydrated, that big dot, H2O, a hydrated iron oxide compound or whatever. So they often tell you what compound it makes, because in actuality it's a mixture and quite complicated. But you must know that we've gone from iron solid to iron oxide. We need a few things for rusting. What do we need? We need iron. What else do we need? Water and oxygen. So these three things are needed for rusting to happen. What things speed it up? Heat? Nope. Good guess though, because heat usually does speed things up. Catalyst? What catalyst? What catalyzes rusting? Salt. Okay, so salt, right? Ships, seawater, more rusting. So salt speeds up the reaction, and what prevents? So the first thing that we could do is a physical barrier. So that would be paint, or if we can't paint it, we coat it in. That's something different.
What's galvanization?
If we can't paint a bicycle chain,
Grease.
oil, we grease it. So you coat it in paint or you coat it in oil. Why don't I oil the iron banister as you walk down the stairwell there? Because everybody get grease on their hands. So it's the same thing, it's just where you're using it. Okay, so I'm going to paint the iron banister and stairwell, but I'm going to oil my pistons in my engine, both of which I don't want to rust, but paint, no, not greasy, and oil lubricates it as well as keeps the rust away. Okay, so that's a physical barrier. We can have a sacrificial anode. Pardon me. It's an anode because it itself loses electrons, right? And do you remember what a sacrificial anode is? Here's your very big ship with lots of crates on it. So it's huge. And what do they do with this big ship? They put a patch on it.
Is that the zinc?
Right? Patch of something that oxidizes much faster. So for example, zinc, for example, magnesium, anything that's a stronger oxidizing, stronger reducing agent than iron is. So in your data booklet, and I should have a data booklet here, ready? In your data booklet, it's lower down than iron is. Okay, so it's a stronger reducing agent, so it's going to be chosen first. Everybody remember that? Except for it can't be lower than water. Like I can't use sodium because sodium's going to end up spontaneously reacting with the water. Oh, that's not good. As soon as I put the boat in the water, done. My patch is gone. Okay, so you can't be something that's going to spontaneously react with water, but it has to be below iron ions or iron solid still. Yes.
There's a question on this exact thing in the practice exam.
Yes.
And it says, like, car manufacturers send a weak electric current from the battery to the frame of the car to prevent corrosion of the steel frame.
Okay.
That said, which of the following methods could not be used as an alternative to the method of corrosion prevention? And the right answer is sacrificial anodes made of copper.
So if you look at copper on your data booklet, and you look where iron is, so where's I'm just not even focused today.
It's below iron.
Copper is below iron?
Oh, no, I think you crossed that one.
Yeah, there it is.
In the question,
So copper's in the middle of the data booklet, and iron is down here. So if I'm trying to prevent the oxidation of the iron will go first rather than the copper.
so steel is made of iron.
Yes. Yes, steel is made of iron. Iron and steel. Steel, iron. Steel is iron and a little bit of carbon. Okay, to just help it not be so brittle, but it's iron. Okay? Okay. So, physical barrier, sacrificial anode has to be reducing agent below iron, and your typical choices are zinc and magnesium. So on your data booklet, you've got iron, you've got zinc, you've got magnesium, and then you've got things that are below water that I can't choose because they will react spontaneously with water. Bad idea. Okay? Magnesium is not a great choice because it over time does react with water because they're so close. So zinc is the choice that we pick in reality. On real ships, it's zinc. Okay, it's cheaper, it's less reactive. We pick zinc. Okay, so that's the patch. It gets across to the other side of the ocean. They take the patch off in Australia. They put a new patch on, and off it goes. And even though you've got this exposed iron here, the oxides will still react with the patch before the iron. So it sacrifices itself in order to save the iron. Sacrificial anode because it's the LEOA, if you were to draw the half reactions. Everybody get this? Okay. Then you've got the third preventing method is galvanization. Galvanization often happens in nails, which it has both the physical and the sacrificial anode. So it is, you coat the nail. So because I'm coating it, it's a physical barrier. Everybody okay with that? But I'm not coating it with paint or oil. I'm coating it with zinc normally. And so therefore, when I hammer my nail into the wall, some of that, if this was paint, if I had dipped my nail in paint, I hammered the nail into the wall, that paint will chip. And then I have a bit of my nail exposed, like the raw iron nail. Now I want a really strong nail, that's why I've chosen an iron nail, because I'm hanging my $10,000 lovely oil painting in my living room. So I want it strong because it's in a nice, big, beautiful frame. So I choose iron, hammer, hammer, paint flakes off. Now I've got exposed iron. And very quickly, that iron will start to rust. And then that rust bleeds on my nice, beautiful white walls and ruins my painting as well. Problems. So I'm going to use a galvanized steel nail, so I still have the strength of that iron, but when I hammer, hammer, and it chips off, and it exposes, this tin offers the sacrificial protection that my boat had. So any oxides that come here are going to react with the tin, or the zinc, pardon me, I keep saying tin, the zinc instead of my iron nail. Everybody get that? And then this nail won't rust for decades. Okay? Okay. So, galvanization, a coating in a sacrificial anode. Then you've got just the sacrificial anodes, which is a patch. And then you've got the physical barrier. Everybody okay with rusting and its prevention? And that we're trying to resist a spontaneous redox reaction. Okay? All right, so that was all of that, all of that, all of that, all of that, all of that. Aha, speaking of spontaneous reactions. So there were two ways, so reaction spontaneity. Reaction spontaneity is a whole little unit. We did an experiment, and by the way, if you go onto Moodle and you go onto the other published videos, you can watch this experiment again. Okay, so we do an experiment in which you take a bunch of metals and you put it in the solution. So I take a zinc metal, and an iron metal, and a copper metal, and a silver metal, and I put them in the solutions. A zinc solution, an iron solution, copper solution, and silver solution. And what I find is some of them react spontaneously and some of them don't. Okay, and when I start doing my ticks and X's, I can then say, oh, the more ticks, the more spontaneity. So without looking at the data booklet, I can't really, I can take a good guess, but it's going to take me too long. This copper is not going to react with anything other than the silver. The silver will not react with anything at all. The zinc will not react. Yes, react. No. I can't remember. Anyway, I'm not going to bother. But the point is, the more ticks, so this is a stronger, are metals reducing agents or oxidizing agents? Metals. Reducing. So this is a stronger reducing agent than this guy because it has more ticks. Everybody okay with that? So I might be asked to list them in order of strength, and I would say copper is stronger than Ag. Everybody all right with that? I might have to build a redox table. So I could end up kind of going, well, if these two, pardon me, let me just redo this. Sometimes they write this a different way. They'll say that copper reacted with Ag plus to form products or a reaction, put that a little smaller, and Ag did not react with any of the ions, or Ag plus Fe2 plus, no reaction. This is just like sentence form of this. And you can still build a redox table with these as well. So we start looking at the spontaneity rule. I think I've come off of the thing here. We start looking at the spontaneity rule with those things. And we start thinking, well, you know what, I'm going to build my, based on my list that it has for me, I'm going to build a redox table. If I build it exactly like the data booklet, I can keep things organized and I know what I'm doing. So I'm going to put my reducing agents down there. That'll end up being the strongest reducing agent. I'm going to put my oxidizing agents over there. That was the strongest one down there. I know that my reducing agents over here are solids because I can see that in my data booklet, and I can also see in my data booklet that those ones are ions. If I were to ask you about non-metals, I can look in my data booklet and I can see that I've got like Cl2 on the left and I've got Cl minus on the right. So if it were to ever ask me about a non-metal, I know that the atom or element will be on the left and the charged anion will be on the right. Does that make sense? So you follow the pattern of your data booklet. And then we look for waterfalls. So if Ag and Fe2 plus did not react, then I know that my Ag solid and my Fe2 plus waterfall is going to go up because it didn't react. So I'm going to write Fe2 plus over here, and I'm going to write Ag solid over there because it didn't react, the waterfall is going up. And then I finish that line off so it looks like the data booklet where I do this and I do this. Everybody okay with that? And then I use the next piece of information. So let's say copper and Ag1 plus reacted. So here's my Ag1 plus. The waterfall is going to go down for copper. I don't know if it's here or here. Right? So something else in my information is going to tell me how it reacts with Fe2 plus. And I read that Fe2 plus and Cu solid was no reaction. So therefore it must be below the Fe2 plus because that one's non-spontaneous. So it's not that one, it's this one. And then I fill it in. Everybody remember those tables? James, are you still with me?
Yeah, I am.
Okay. Okay, so that was this whole big section about reaction spontaneity. They will ask you a question about this on the diploma. They will. So make sure you've practiced a few. Okay? And they ask you in different ways, build a table, list the things from strongest reducing agent to weakest reducing agent, list the oxidizing agents from strongest to weakest, whatever. They ask you in a lot of different ways. They give you the table, they give you a bunch of sentences. Each of them are the same thing. And it will be on the test. Okay? So make sure you look at it. Okay, so blah, 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 blah. After that, we did predicting redox reactions. Okay, so next little subtitle, predicting redox reactions. By the way, just because I'm thinking about it, how do you tell if it's a redox reaction or not? Because that's often a question, and Connor asked me this morning about that. So sometimes they say the following, which of the following is not a redox reaction, right? Or which of the following is a redox reaction? What are you looking for, Connor? Do you remember what we said?
Change of oxidation numbers.
Right. If it changes oxidation numbers, it must have transferred electrons, and that's a redox reaction. Okay? So you're looking for a change in oxidation numbers. So has a double replacement reaction like this, this is a made-up question because it doesn't work. AgCl and CuNO3. Does this reaction, is this a redox reaction? Very fast without doing your oxidation numbers, because that's going to take you too long. Can you see that this is iron 1 plus, or silver 1 plus? And that I still have silver 1 plus over here? No change. Can you see this NO3 minus? Still NO3 minus? No change in oxidation numbers. Still copper 2 plus, still copper, 2 plus, no change in oxidation numbers. Chloride ion, no change, so no change. So this is not a redox reaction because there can't be any change in oxidation number because it's the same ion on the left and the same ion on the right.
So if they're different, that means.
Right, so let's do a single replacement. Let's go AgNO3 plus sodium. And the sodium will replace the silver, and it'll look like this. So silver solid, silver ion, sodium solid, sodium ion. In order to go from sodium neutral to sodium positive, it must have done something with its electrons. Right? You don't even have to think about what it's done with the electrons. You just have to know if it's changed its charge, it must have played with those electrons, which means one of them is Ger and one of them is Leo. So it means redox reaction. You can do all the oxidation numbers, and you might if it's a tricky one, but if you can see it like this, just use it. It wastes time doing all that. Like, that's a lot of work, all those oxidation numbers. Okay? That's sometimes on there, not always. All right, so predicting redox reactions. So blah, 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 and blah, blah, blah are added. Okay? Tell me the net ionic equation. So the first thing you're supposed to do with all these blah, blah, blahs is you're supposed to pull out the species, and you make a species list. So if it's a weak acid, they stay together. So like CH3COOH stays together, just like it does in the acid unit. Just like it does in the acid unit. If it's a strong acid, we pull them apart, like H3O plus and Cl minus. Or actually in this unit, we stick to the H plus. Okay? If it's an ionic compound and it's soluble, then we pull it apart. So Na plus and Cl minus. If it's an ionic compound and it's insoluble, we don't pull it apart. So like MgO. Just like we do for bases, by the way. So Na plus and OH minus would get pulled apart, but aluminum hydroxide would not be pulled apart. Do you remember doing that in the bases unit? Pull apart, keep together. For whether it's going to be a strong base or a weak base. Solubility. Okay? And molecular compounds never dissociate or ionize. They always stay together. So that would be like H2O stays together. Another molecular compound, sugar, C6H12O6 always stays together. Everybody okay with that? A common soluble ionic compound that they pick is potassium permanganate and potassium dichromate, Cr2O7 2-, because they are very strong oxidizing agents if they are acidified. Okay, so you list your species. That's the first thing you do, and that's a little trick about how to list them. Then once you've listed them, you then pick your you look at the whole list, and you pick your strongest oxidizing agent, and you pick your strongest reducing agent out of the whole list. So if I had potassium permanganate there and it was acidified, then I would have acidified permanganate be my strongest oxidizing agent. Okay? And my strongest reducing agent is, well, whatever. I'd have to have a look at the data book for this example. If it's aqueous, I always have water present, right? A solution of water's present. Water's one of my species. Acidified equals acidified means I have H pluses present, and a basic solution would mean I have OH minuses present. Okay, any questions on that? Once I'm rubbing it under the board, so I've got some space. Okay, so once you've picked your strongest and strongest, and how do you know strongest and strongest? You look at your data booklet. The strongest reducing agents are down there, and so then you work your way up until you find a species, and you stop, right? And you write that line down, whatever that line is. So let's say we had some zinc solid that, you know, at the blah, 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 it said zinc solid was dumped in an acidified potassium permanganate solution. So I've got zinc solid, that's my strongest reducing agent, acidified potassium permanganate solution, there's my strongest oxidizing agent. So I write down the zinc, because I found it, bottom right hand corner, work your way out, there's zinc, arrow, zinc 2 plus 2 electrons. How do I know that? I just copied, not a big deal. Now I'm done the reducing agent. I go up to the top left hand corner and I try to find my strongest oxidizing agent. Oh, look at it's here, it's this acidified thing. So then I just copy again, O4 minus plus 8 H pluses plus 5 electrons. How did you know 5 electrons? I'm just copying. Goes to Mn2 plus, etc. And now we're back to day 1 lesson, where I'm looking at my electrons going 2 electrons lost, 5 electrons gained. Those don't match. If I give out donuts at the cafeteria, our cafeteria doesn't sell donuts. If I give out scones at the cafeteria, if I give out 2 scones and I've gained 5 scones the students have, that doesn't make sense. So actually the cafeteria has to give out 10 scones and the students have to gain 10 scones. That makes sense. This has to happen 5 times, that has to happen 2 times. I write my net by bringing that 2 all the way through. Done deal. Do you need me to do it? Or are you okay?
I'm still on the line.
Yeah. Welcome to a whirlwind.
Well, no, I understand.
Okay? So, if, you know, like put an asterisk beside it so you know to look one of these questions up to do, to work through slowly. And then you've got your net ionic equation. And sometimes they ask you for the net. Sometimes then, if they say the zinc was added to the acidified potassium permanganate solution, it then gives you some information, like some volumes on a burette and some concentrations. And it asks you to solve for the concentration of something. And then we just actually are just doing stoichiometry, normal science 10 or Chem 20 stoichiometry after that net ionic equation. Okay? So how does this present itself in the diploma? Well, very rarely do they make you do the whole thing. Sometimes they'll say blah, 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 blah. What is your strongest reducing agent? So you list your species and you say the strongest reducing agent is zinc. Sometimes they say, which of the following is your net ionic equation? So you list your species, find and write your net, and then that's the answer. Sometimes they give you the net, so you don't have to even do the species list, and then it becomes a titration question. Okay? So there's a variety of ways, but that's the whole full meal deal if it was a written response, 10-mark question. Okay? Sometimes you have to make up one of your half reactions. Okay, so if it's not a species list, or pardon me, you write your species list, and they tell you that your reducing agent is the metal, and they call the metal just X. So a metal X was reduced, or was the reducing agent, pardon me, was oxidized. Blah, 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 blah. Then you sometimes have to make it up. So this becomes X. They tell you the ion is X3 plus, so X3 plus. Then you've got to think it must have lost 3 electrons. Everybody understand? So sometimes you have to make it up if it's not in there already, and they'll give you X or they'll give you cadmium because CD isn't in there, or at least it didn't used to be. Oh, it is in there. I don't know, whatever, right? They give you one that's not in there. Chromium. Is chromium in there? Yes. Huh. Anyway, you get the point. Okay? And you've got to just make it up. But there'll be simple ones like this. Happy? Moving on? Overwhelmed?
Yes.
Put an asterisk beside it and do an example slowly after we finish talking. Oh, and then that lovely diagnostic tests, right? Oh my gosh. Okay, so by now you should be okay with these diagnostic tests a little bit more. So you're looking at the products that are made. And 4 waters. Okay. So what products are made? Well, let's go back to the zinc 2 plus. What does zinc 2 plus look like? Might have a color, right? It might have a color. So you go and look up the color. Oh no, it's colorless. Oh, that doesn't help. I can make water. I don't really, there is a test for water, but you know, it's a solution. Mn2 plus, does that have a color that might be different from the Mn4 plus? Ding, 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 ding. Color of Mn4 plus is, you can look it up, but you should know. Where do you look it up? In the data booklet? At the back, she says, with a bit of hesitation. Yes, question 11. Or page 11, I mean. Purple. Remember that bright purple that we've used quite a few times now? And purple changes to Mn2 plus is colorless. You can find it. So one diagnostic test that I have got my net reaction is all my purple will be used up and I'll have a colorless and colorless solution. Does that make sense? That's one diagnostic test. Bubbles of gas. Students always are like, bubbles of gas. Do I have any gas anywhere? No, I'm not going to see any bubbles in this reaction. So bubbles of gas isn't one I'll use. Will the metal zinc disappear? Metal zinc, will it disappear? Like, I mean, will it dissolve? Will it go away? Will I see it anymore? They'll probably say, right, correct. So they'll probably say the zinc will decrease in mass. That's the best way of saying it. Or my zinc solid will not be seen anymore? Sure, because it all becomes zinc 2 plus. Everybody okay with, everybody get that? That's another diagnostic test I could have here. What happens to my H plus? It's being reacted, right? What's H plus? pH. So is my pH going to be high or low to begin with? Low, because it's an acid. If I'm using it up, the pH is going to go closer to neutral, because this is neutral. So any of those diagnostic tests work. I am not, like, it's not because I've seen this reaction before that I can do these things. It's because I'm looking at the species that are here and going, if this is going that way, it must be used up. It must, if this is a solid, it must be disappearing, or the mass is going to decrease, is the nicer way of saying it. If I'm a H plus is being used up, that means the pH is going from acid to neutral. Oh, I can do that. So it's not that I've seen this, that I've experienced it, that I know it. It's because I can just put it all together. What does this look like? What does this look like? Okay, and that's your diagnostic tests. And by now you should know Cl2 gas is green, Cl minus would be colorless. What other ones aren't in your data booklet? Br2 is, Br2 is a variety depending on how aqueous it is. So it's brown, a really dark red brown in its most concentrated, like if it's pure Br2, But then if it's a solution, then it's orange, and if it's incredibly dilute, then it's yellow. Can you see how that's just a, you know, dark, like a lighter version of each other? I2 solid is gray. You know these off by heart? They're not in your data booklet. Okay, write them down. Good job. So gray if it's a solid, and if it's aqueous, iodine is biology. Iodine solution. Sometimes it's purple. In fact, I think actually more often they say that it's brown.
What's that say about that?
Purple gas. Huh?
What's that say about brown for I2?
Gray solid. Also common ones, Cu2 plus ions are blue, right? Like copper sulfate, etc., etc. I'm just going to keep going now. Okay. Could that be the end of that first chapter? Indeed it is. Okay, so, good? In fact, it's not quite. Oxidation numbers, we haven't done. Okay, so maybe the last thing on this chapter is oxidation numbers. I'll have a keep flipping and see if I see anything else. So oxidation numbers. There are rules to these things, right? About what you do first, second, and third. The shortcuts, though, that we experience after we follow the rules religiously and then it just becomes sort of like inherently ingrained in us, is that we kind of go from the outside in, right? For the complicated ones, we go from the outsides into the middle. So for something like, I don't know, sodium perchlorate, I would do sodium and oxygen first and then chlorine last. Right, I go from outsides in most often. So it's a generalization to the rules. Also, the rules elements have an oxidation number of 0, which, hey, ties in with that Unit 1 concept about, you know, energies of formation, enthalpies of formation, products minus reactants. The elements there were 0, 2. Okay? So, 2 zeros for elements. So the element's oxidation number is 0. For an ion, the oxidation number is that ion charge. So here, you should be able to see that this is actually sodium 1 plus and ClO3 minus. And so therefore, the sodium's oxidation number is 1. We do oxygen first, -2. 2 times 3 is -6. So this must be positive. Oh, it has to add up to -1. So this must be positive 5. So another rule is if you have an ion, complex ion, a polyatomic ion, the charge of that polyatomic ion, the number of the oxidation numbers better add up to equal that charge. So if I have SO4 2 minus, whatever my oxidation numbers end up being for S and the total of O's better equal -2 because of this -2. So let's do this one. So I've got oxygen is -2, 2 times 4 is -8. The sulfur must be positive 6 because they have to add up to the -2. Yes?
What do you mean by ion arrow oxidation arrow?
The oxidation numbers
Yeah.
have to add up to the total charge.
The one above.
Polyatomic ions have a charge.
The one above that.
Sodium ion, simple ions, their charge is their oxidation number. So this guy's oxidation number must be +1 because it has a charge of +1. Calcium is a 2 plus, so its oxidation number must be +2. Same with non-metals. Br minus must be -1. That's what I meant. Okay, and so there's a blah, 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 blah. Oh, yes. And then we get into those bridges. So sometimes you have a reaction, I don't know, zinc, just because. And in this reaction, you are going to, zinc plus that compound, which I've already found the oxidation numbers for, goes into
Junior class change.
a bunch of stuff. So like zinc 2 plus, etc. The oxidation number of that element is 0, so I'm going to do a bridge here. So if I've gone, and I did bridges at the beginning actually of this little chat. So if I've gone from 0 to positive 2, it must have lost electrons, which is oxidation. Therefore, this is my reducing agent. And let's say I form Cl2 there, so I've gone from 0 to 0. So if I've gone from 5 to 0, I must have gained electrons, which is reduction. My number indeed was reduced. And I must have gained 5 electrons. And here I've lost 2 electrons. Now I have 2 half reactions, essentially. They're just sort of tucked together, but I have 2 half reactions here, where this one is losing 2 electrons, this one's gaining 5 electrons. Hey-ho, that doesn't make sense. Back to the cafeteria. I have to gain and lose the same amount. So that must mean that this has to be multiplied by 2, and this has to be multiplied by 5 in order to have them equal each other. So I bring this number up. I need 5 of these half reactions. So if I multiply that through the brackets, if it was just by itself as a half reaction, there it is. Multiplying that 2 throughout those brackets, if it was a half reaction like it was 10 minutes ago, I would end up with a 2 here and a 2 here. Oh look, I already have 2 there. Because of the little 2. Everybody okay with that? So that's multiplying those half reactions. So now this is not a viable reaction. I'm not even pretending that it is. So I'm just going to say to you, here we start looking at major OH, where we balance our major species. I've just done that. In this case, I've got zinc, chlorine. Oh, sodium's also a major species. Oh shit, I didn't even write sodium over there. Let's just put like plus Na pluses. So I look here and I'm like, oh, plus Na pluses. I have 2 Nas over there. I need a 2 Na pluses over there as well. Make sense? So my major. Then I balance my oxygens by adding water to balance my oxygens. So I've got 6 oxygens on this side. I need to add water to the other side to balance the oxygens. How many waters am I going to need? 6 waters. In order to have 6 oxygens and 6 oxygens. Everybody get it? Yes?
Can you explain why you didn't put 2 as a coefficient of Cl2 on the right side? Is that just because we're balancing?
Why didn't I put a big 2, you mean?
Yeah,
Because 2 of these will make 2 of those. Oh, they're already stuck together.
Oh, so just because if you multiply it by 5, that doesn't mean you have to put the...
I need to have 5 of them.
Oh,
Okay?
Okay.
So I'm going to add water to give me my oxygens over here, and then the H's are balancing charges. I'm going to add H pluses to balance charges. So I look at my charges, and over here it's neutral and neutral. Over here it's 10 plus and 2 plus, so I've got 12 pluses. So on the left I need 12 pluses in order to make it work. I better have 12 hydrogens as well. 12 hydrogens, spot on. So that worked out for us. So major species first, oxygen for your waters, and then charges with your H pluses. This might not be a perfect example because I've kind of made it up on the fly, but yeah, yes.
Do you mean like you balance your hydrogens and then your charges, or is it at the same time?
You can, they both at this, well, I'm going to say at the same time. So you choose which way to do it, but as Connor and I came up with, if you balance your hydrogens and then your charges didn't work out, you've done something wrong. So go back and figure out what you did wrong.
So you balance your hydrogens by adding hydrogens.
Yes, you can do that. Yes, balance your hydrogens by adding hydrogens, fine. Or balance your charges by adding hydrogens. They should be the same number.
Can you add them to either side?
Yes, you can.
Like water and hydrogen?
Yes, you can. Okay? Now, if this is a half reaction, that you're asked to balance with oxidation numbers. This is a net reaction. I have something losing and something gaining, it's net. If it was a half reaction, I need to have electrons in my half reaction, right? Blah, 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 plus electrons, arrow, da, da, da. So we need to put my electrons somewhere. So you follow the same idea, but tucked into there is major EOH. So you balance your major species, then you balance your electrons based on your oxidation number. So if your oxidation number says that you lost 2 electrons, you lose 2 electrons over here. Does that make sense? So major EOH. It would be worthwhile practicing these, except for this. Let me tell you this. If you are in the space where you are just passing this course, you are just passing the diploma, you don't really need to stretch yourself, you don't really need to get into U of C engineering program. All of this stuff may, and only may, be on the diploma. And if it is, there's only going to be one question on it. This is probably the hardest thing in Chem 30, I think, for students. Okay? So, if you are just passing, when you get your final marks back and they're not great, this is not your concern. Maybe on the 26th of January, you might be ready to look at this. Now, if you are sat at an 80 and you want to push it to a 90 and you want to keep it at 90 and you might want to play your plan B after the NHL in order to get into business school and you want to go to Harvard's business school, this might be the one question you want to focus on because you've nailed all the other concepts and you're ready for this one. Everybody understand it? Everybody's capable of this. It's just when are you ready to digest it? Okay, this is a gamble as to whether it's going to be on or not. So if you're not ready to digest it, you might want to gamble to not look at it. Everybody get that concept?
Did you say the final marks were good?
No, I said if you get your final mark back and you're like, wow, I am struggling to pass this course,
Oh,
then this is not your concern. Something like those redox tables, which I said are absolutely on here,
yeah.
that's your concern. Nail those first. Okay. So, and then that's where we end that chapter. And then we begin looking at, and this will be a lot shorter because I'm getting tired and you are dying over there. So, this is where the next chapter comes in, where we look at voltaic cells and electrolytic cells. Electro,
I think it's a Y.
L-Y-T-I-C cells. Okay, so voltaic cells are spontaneous, electrolytic cells are non-spontaneous. Voltaic cells are drawn with a voltmeter there, or sometimes nothing there. Electrolytic cells have a power source, or a battery, or a generator there.
YouTube. I like the song.
So in a voltaic cell, they have to be separated.
Yeah.
So they're sometimes separated with a porous cup, sometimes they're separated with a salt bridge, but they have to be separated. Whereas these ones don't have to be separated, but they can be separated. Okay? So electrolytic cells can be separated or don't have to be separated, whereas voltaic cells absolutely have to be separated. So voltaic cells are your batteries because they are spontaneous. When I plug that into my calculator, I want my calculator to spontaneously work. Electrolytic cells are charging your battery, recharging your phone, creating the sodium chloride to give me back my sodium metal, which very easily reacted with my chlorine green gas spontaneously. But actually I want to do this so I can go and sell that to labs so that they can then add it to the water. Right? So if I have to force a reaction to happen, I need to do this way. This is going up the waterfall. This is going down the waterfall. Always, 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 Leoa and Gurk still apply. Yes?
So for voltaic, you're looking for the longest waterfall, and electrolytic, you're looking for the shortest.
Yes and yes. Yes, that's true. But Yes, fine. Electrons flow from the anode. Electrons flow from the anode to the cathode. In both cases.
Is the anode
Hmm?
positive or negative?
Yes, so the yes, that's right. So voltaic cell, the positive voltage, and this is negative voltage when you calculate your E volts. But you're right, the anode over here is, and I always get this mixed up, especially when I'm doing a whirlwind stress. The anode and cathode have charges that are different on both of these. The cathode is, cations are produced there. So this is positive and this is negative, and anion here is positive and cation is negative. Can somebody double check that? Yep.
Didn't we do like a table?
Yes. You be very wise to have a look at your table that we've already done on this a million times. Not right now though, Nick,
I was just like,
but definitely would be good to look this up. Electrolytic cells. So I think that's about it. Once you've memorized that table, you then just apply it to a variety of examples. Electrolytic cells are branched out slightly where we talk about specifically electrolytic cells are used for electroplating. So that's forcing the Ag plus to become Ag solid, and then I have a silver plated trophy. Right? Or having my chromium 3 plus plate onto my car bumper, and then I have a chromium plated bumper, but it still has the strength of the iron underneath. Right? Oh, by the way, that sounds a whole lot like galvanizing to protect that bumper. Yeah, because they're the same thing. So galvanizing is electroplating. So we looked at electroplating for electrolytic cells. We also looked at the chloride anomaly. So if I've got chloride in my solution, it will react before the water does, even though the waterfall from my, whatever it is, I don't know, let's pick a Fe2 plus. So Connor was just saying that the Fe2 plus and the water here have the shortest waterfall, so those are the two things I should pick for my Leoa and Gurk. However, the chloride anomaly says that actually chloride reacts, not the water, if I have it present. So I end up forming chlorine gas. How do we know that? Because we see it.
Is that only for electrolytic?
It's only for electrolytic, yes. Yeah.
You're the shortest waterfall to go.
Note for this, I have my strongest reducing agent, which would be the furthest down, and my strongest oxidizing agent, which is the furthest one up, so therefore it should be the longest waterfall because of last chapter's rules. Right? Strongest, strongest. You would be wise to have a look at that that thing. One more thing in this unit is your Faraday's constant. Number of electrons equals IQ over F.
I didn't get that. Like, I just didn't understand.
IT, thank you, which is Q. Okay, so what you need to do is you need to find an example on that, and you've got, like, I don't know, copper 2 plus reacting with 2 electrons to form copper. This is the number of moles of electrons. It's a 1 to 2 ratio, so let's say I have a mass that's made here of 5 grams. I go mass over big M to get N. It's a 1 to 2 ratio here, so I multiply that by 2 to get the N of electrons, which goes in here. Faraday's constant is a constant. It's in your data booklet. This is how many amps that the current is running for. This is the time that we're running it for in seconds. So let's say it would be how many seconds do I have to run my 3 amp battery for in order to produce 5 grams? So I'm solving for time in seconds. It's told me 3 amps. Faraday's constant I just look up. Number of moles of electrons I take from that mole ratio there. So it's stoichiometry with a new formula. It'd be wise for you to do one of those. And that's, I think, the end of Unit 2.